Yeah, great. Now, can you hear me?
Yes.
Okay. Did I give any problem in the last class?
Uh,
No, right? Okay. I could remember, as far as I could remember, the last thing which we discussed earlier in the previous session was one problem. Basically, we discussed about the growth of current, right? Growth of current in RC circuit, RL circuit, RL circuit. Look it now. Wait, this is about the RL circuit, okay? So what was the equation we got? We simply got an equation where I have a current which was dependent upon the time, and the dependency was something like this: 1 minus e to the power negative of something. What is it? T by tau. What was the value of tau right now? Where tau was equals to L by R. Could you remember that? Yeah, Kirtna, could you remember that? You should actually remember this. Why? Because in upcoming chapter we are going to discuss about RLC circuit, okay? RL circuit, LC circuit only, and like different combination of this RLC, okay? So for single R, you already know simple L, you know, C, you know. You might be not knowing this, you might be knowing RC also. We'll be discussing this. Okay? We'll discussing multiple things, so you should actually knowing this thing very well to cope up with that chapter. So yeah, Kitna, are you really clear with this concept, this formula, which we discussed in the previous session? Ketna, are you clear with this concept? And yeah, okay. So let's look at this configuration once. You had this inductor, okay. You had a resistance and you had a key. Initially, when the circuit was closed, there was no current in the circuit. You simply had a small battery with potential V. This is inductor R, this is this. The moment you switch on the key, at that moment, at the time t is equals to 0, when we closed, in that case, after t positive, or just at t is equals to 0, plus current was current was 0. Why 0? Because there wasn't this kind of inductance like EMF produced due to this, which is decaying by the time. Okay, so you can actually remove it like at t is equals to 0, this was acting as this. That circuit is open. This was acting as an open circuit. Understood? If you can remember, this open circuit conditions happens in case of capacitor, but when you let this current pass through the capacitor for a very long time.
So
Okay,
can you explain it
understood
again? I
that,
got disconnected.
what happened?
So can you explain it again? I got disconnected just.
Okay, fine. Sorry, I thought you not interested. Look it now. Could you remember that in case of capacitor, let's say this is my capacitor, okay, this is the resistance. If I used to give current, initially when this is not charged, what happens is it starts charging, and by some time, which is goes to infinity, when this gets completely charged, then current starts like current gets stopped, right? So in that case, we generally say after a very long time, this capacitor act as an open circuit, right? If you could remember in RC circuits, could you remember that? Why we are saying this? Because from here there won't be any current flow to this side because of this capacitor. Understood? Because its potential is similar to this at this stage. But this condition happens in case of inductor at the very early stage. If you can remember, if you just put the time t is equal to 0, current is 0. What does this mean? At a very at t just positive. It is not 0, it acts as an open circuit. Understood? At the moment of closing the key, closing key, inductor act as an open circuit, as open circuit, having maximum reverse potential, maximum reverse potential, okay? And after a very long time, after long time, it acts as closed circuit, completely closed circuit, a single wire. Okay, after a very long time, the effect of this inductor goes away. If you see, if you put the time t is equal to infinity, okay, this thing will go zero, I is equal to I naught, the maximum value, okay? So you can actually see that. So approaches to infinity, in that case, the circuit looks like this, okay? Here inductor was there, and it is looking like this, and here inductor was there, and this is acting as a closed circuit, okay? This is acting as an open circuit, and here it is acting as a closed circuit. Clear? Understood, Pratna, this part?
Yes.
Yeah. So that's the two result you need to remember, okay? Because when we are going to solve some problem, just a second, Pratna, all right, Pratna, if you just understood this part, let me know. We can move to problem solving part, okay? It will give you better understanding. If you understand this previous thing, which we discussed a little bit about, is it clear?
Yes.
Okay. So assume we have a simple circuit, okay? This is an inductor, okay? And this is a battery as well. I'm saying this is R1, this is R2, and this is just L. So I'm asking, and okay, before this is a key, okay? R1, R2, and this is L, okay? You have to calculate current across R1 and R2. Okay, you have to calculate when first case is when just just after closing the circuit, closing the key. Okay. This is one thing. After very long time, a long time. These two things you need to calculate. Now, can you try it once? Just calculate it. Let me know answer. For simplicity, also do one thing in both cases and overall current. And overall current. Overall current means to say what is the current passing from this part. Okay? This is overall current. This is current getting in I2. This is the current getting in I2. So you need to calculate them. Try it once, Kirtana. I'll get the solution afterwards. This point means the circuit is closed. The point is open. It means this circuit is open. Okay. This is basically a small switch or key you can call. Current it is closed. Kirtana, if you're trying, let me know.
Yes, sir.
You're trying it. Actually makes sense. Just think of it. We have discussed this thing earlier also, so it might be very good. It may get very easy for you to solve. Yes. Kirtana, should I get the solution for this one?
In instance.
All right. So let's look at this one. Okay, Kirtana. So the problem says a very simple idea with you that I think it says. So the problem simply says that you are given and this thing and another is this and this. Okay. So let's come up with both of them. If I ask you what is the condition just after closing the key? Okay, just after mean to say maybe the time is equal to zero when the process has started. Okay, so assume that kid now this is one wire, this is another wire. Okay, this is the thing, and this is a potential battery, right? From this, some current I will be coming out. Yes, it will be coming out. The maximum current maybe, right? Out of this maximum current, some amount of current might be going here. The rest of the amount of the current will be going here. Yes, it is the case. Because why I'm saying this? Look, a very simple idea. Both of them have a same potential. Potential across this and potential across this is same. Understood? Potential across both of them are same. Then what does this mean? A very evident idea is here there's the presence of inductor. Okay, it means the current inside is always growing. It is going to be a growing current. So whatever the in this circuit, this I1 will be very simple. For the A part, I1 will come out as what is that? Total potential divided by R1. This is the current we are going to do. This is maybe V, so this is R1. What about I2? If you could remember, our I2 depends upon the time. So I'm saying just start. So this is dependent upon time. Why it depends upon time? Because of presence of this inductor. So I'm saying potential across this is something V. So this is I naught maximum current. What is going to be the maximum current for you? Okay, so maximum current will be something like yeah, that's V. So this will give you something around V naught divided by whatever the value is. 1 minus c to the power minus t by L by c or something, tau you can call it as so L by R. This is what we are going to get. So if we actually go and substitute the value as 0, which is a very small starting. So I2 comes out as V naught by R. Is it? No. The answer will be 0. Okay. This will come out as 0. Understood? So how the circuit will look like when you just start the thing. It will look like, I have already told you. If you look at this, at the moment of closing the key of the inductor, this. So at the very moment, at the very start of the moment, this looks like an open circuit, right? So here also the same. The moment you start, this is an open circuit. So it looks like this is R1, this is R2 is there, but it's not complete circuit. Okay? It's a just open breakdown circuit. So what will happen? The current which wanted to go, it won't go because it's a open circuit. Okay? But after, so you can simply say I2 will be 0 and this will be as it is because of the potential, whatever the value is. Then you actually come up into the picture of yes, this is the B case. What is the B? I1 will remain the same, right? There is no difference. What about I2? Now your time is infinite. Put the infinity, the time will go as V naught by R. Okay. I already told you after very long time, after the key, after very long time, it acts as a closed circuit. It means inductor is not going to show its effect after very long time. It will like this. Only in between the time it actually shows an inductor. Understood? It actually shows its property of inductor for varying different current. At the very start, breakdown circuit or something like this. Okay. So here if I ask what is the I, total current I1 plus I2, that is V by R1. Here it will come out as V naught V naught. So it will come out as I is equals to V naught R1 plus R1 R2 divided by R1 plus R2. Okay, you can just try to add it with and you will get this thing. So Kate, now just let me know if you understood this problem.
Yes.
Okay. I hope this really makes sense a little bit. So mm, okay. So this is the thing here now we can discuss. Let's say I'm giving you another situation, okay? This is switch one. Okay, there's an inductor in between. There's another switch. So look, this problem is very simple. It's not actually simple. Look what happens is, I am saying at the very start both of them are open. What we are going to do is we are going to close it. So I'm saying initially both switches are on, both switches are open. Okay. What you are going to do first, switch S1 is closed and achieves steady state. Okay. After that, S1 is open and S2 is closed. Understood my point? What I'm like, initially everything was open. It was like this is also open. You did something, closed it, let the current because now this is a complete circuit. So in this complete current is going whatever it is. After steady state, what is the steady state? After very long time. Okay. After very long time, you just turn it on or off. This you made it off. Okay. Then whatever the condition was going with this inductor that gets stored, now you just turn it. Then what is the next condition after? This is what you have to calculate. Current after this, after closing the switch on. So okay, now you have to calculate open and S2 is closed. Find current in the circuit across R just after S2 is closed. This is the problem, kidnap. You can try it once and get me the solution. Yes, Kirtna. So, have you solved it or I should explain it? Kirtna? Yeah, Kirtna, please let me know. Should I explain it or you have got the answer? Okay, I'm going to explain it if not in a way you have got it. Look, so when you just turned on the when S1 is on, okay, and you let the current flow, what happened? This is something like this. It is acting like this. Current is flowing like this way. So after, like, there won't be current in this because this is open. So what will happen is this is going in this way. Current I is there. So I said after a very long time, what does this mean? Steady state. After a very long time, what is the current flowing to complete circuit? This thing is going to act as a this simple this. Okay, it means single wire. So is there any resistance? I actually forgot to keep a resistance over there, but assume the resistor is present. So at this moment, what is the current after steady state? Current comes out as E by R. Okay, that's the point. It means current flowing in this is E by R. Okay, this is I. Now what happened? You just turned it off. Okay, the moment you turned it off and you close it, what happened in this is you got into a new picture. What is that picture? That at this instant, the moment you close it, this wire got closed. Okay, there's a potential over here. This is a resistance over here. And but the moment you close it, what happened at that moment? This inductor had a current across it. What was that inductor? I is equals E by R. Clear? E by R. So what will happen this moment? You know pretty well that whatever the changes will be there, whatever the changes at the very instant, whatever the changes, if I ask you what is the change at this instant, at the moment, what is the current? This is the current, right? After this, if I ask you, you are saying let's have a more current from there. If I remove this effect right now, if I remove this effect for now, can I say the current has zero? So this P by R, this EMF will try to induce some current. You know, this new moment, this will provide some current, but you know the current is at very start is zero, right? Current at the very start is zero. So the current due to this at the very start is going to be zero, but it already had earlier current. What was that value? E by R, previous part. Okay, this will get vanished because you are not going to have a change in this. This is going to vanish after this. Understood the point? This is going to vanish after some time. So at this particular moment, the current is still flowing as E by R. This is new current, and this is earlier. Okay, so current is E by R. Understood my point? At the very start, at the very beginning, the state of an inductor cannot be changed. It remains same. So in the previous cases, if you could remember, when the very start, here no current was there. So the moment you turn on the switch, current is still zero. Because earlier current was also zero. In this case, you had some earlier current. So it will maintain itself, okay? That is the thing. So Kirtna, please let me know if you're clear with this concept. Okay, so if you could remember, if you're clear with this, I'm going to give you another problem. Time is not that much, so I'll explain it directly. Please let me know if you are clear with the above one. Hmm, I don't know whether I can hear you. So, Krishna, look, you are given an EMF, okay? In this, you need to calculate, find current in circuit, or assume this is current I, okay? This is current I, sorry. This is current I. Find I at any time. This is current I, okay? Time t. So how you can calculate it? So Kirtan, look, let's say from here the current I is going, okay? I am saying I1 current is getting inside it and I2 current getting inside it. Okay. So you can actually say that, sir, that I is equals to I2 plus I1. Yes, I can say that. Okay. So what is I2? Okay, I1 and I2, right? Sorry, it should have been written in the form of I1 plus I2. What is I1? I1 is growing current. Understood the point? It is going from 0 to some higher value. We are unaware of that higher value. So you can we write it as a perfect value. So what you can actually do, let's start a complete circle as a KVL. Let's apply a KVL rule. So I'll be starting with this. I'll say E. Then I'm going this. You are going in the direction of current, so we have already seen IR. So we are going to do for this also. We are going to do for this also. See, I am going to do for the other circuit first, upper one. Okay. So I am going to go this way. So this comes out as negative. We are going in this direction. Understood my point? You are going in this direction. What is this I2 times of R is equal to? What is I2? This I2 is basically I minus I. Okay. This is what you are actually getting. So I minus I. Sorry, this is I1 times R is equal to 0. So if you rewrite this thing in a better way, negative was already the negative comes. So sorry, it should be this capital. Yes, cancel. No, you can't actually cancel. This becomes minus plus I1R is equals to 2 times of IR. Okay, this is some equation we are getting. We will look at the equation of I1R in later on times. So let's talk about this. Another equation. E minus we are having IR minus I1R. What about this? What about this? We know what is the potential across it. We are going with this. So directly write it as LDI by dt. This goes here. Wait, now, is this clear so far? Kirtana, can I say that from here I can get one equation that IR is equals to E plus I1R by 2? Yes, I can say so. Look, because, why I'm doing this? Because, okay, sorry, this should be I1. Okay? In this whole equation, I have I1, I1, I1. So I will actually try to remove this IR. Okay? So you got something like E minus E plus I1R whole divided by 2 negative I1R minus LD I1 by dt. Clear? This comes out 0. So let's solve it once. E by E minus 2. So E minus I1R by 2 minus I1R minus LDI by dt. Okay, so this is 0. Finally, if you write in a better way, the equation comes out as E minus I1R minus 2 times of I1R minus 2 times of LDI by dt goes 0. Later, let me know if you are clear with this till this step, okay? Sorry. Yeah. Can we can you calculate the rest of the part from here? I think you should actually. You should be able to calculate from here. Look, a very simple idea also. E minus 3IR multiplied by dt because you take this side. 2LDI. So dt is equals to 2LDI1 3 divided E minus 3I1. So what is the equation of I1 you are going to get? It will be t at some random time. From here you are going to get 2L outside log of this is E minus 3I1R, okay, divided by negative 3, I think negative 3. This is what you are going to get. So in a better form, if you just keep it over here and write in the form of logarithmic, what you are going to get T3R by minus 2L is equals to log E minus 3I1R. So this comes out as it now. E minus 3I1R is equals to e to the power minus 3t. So from here, if you solve it further on, you will get, sorry, have I skipped something? Did I skip something? Is something wrong with it or what? Over there. I is there, is there. Yes, I think everything's fine. So from here, you can actually make it like 3I1R is equals to E minus E, sorry, 3TR by 2. This is what you are going to do. Please let me know if you want. So you got the final equation as I1 is equals to 1 by 3R E minus. This is the equation you are getting to. Clear?
Yes.
Okay, sorry. Actually, when you had to integrate this thing on both sides, you will be going from current I1, sorry, starting from 0 to some higher value, some I, okay, I1 basically. Or I can say something very higher value. So by doing that, you'll be getting bottom as E itself, okay. So this will result to E here, and this will be X. So it becomes E by 3R E minus, sorry, E already common. So you are left with this is the equation. So Kirtak, you see you have got an equation of I1. Okay. So you have both of the equation to calculate. Can you calculate the rest of the things?
Alright.
Yeah, Kirtan, can you solve the rest of the two part?
Alright.
Yeah, look, we have got everything, okay? You know the equation is I is equals to I1 plus I2, right? If you just look at the equation, what happens at the very start? At the very start, this is acting as a open circuit, something like this, open circuit, okay? After some time, after a very long time, it is going to act as a complete thing. Understood? So you can just think of it in a way. You have got an equation for this. What about this and what about the rest of the thing? You just need to think about that part. I hope you'll get the answer by this. Yeah, Ketna. So let me know. Is there any doubt, Ketna? We'll end the session by this. Okay. Okay? Further from here, you need to calculate I2 and I. Okay. So you can take this part as a homework if you want. Clear, Ketna?
Yes.
All right, Ketna. So you can actually try that as a homework. From my end, that's all for today's session. If you have any doubt, please let me know.
No.
No doubt, right? All right, Ketna. So we can actually end the session by this.